Sections 5 and 6 are about matrices and matrix operations, multiplication, addition, and so forth. A matrix is basically a rectangular array, M by N matrix, M rows, N columns. Here's some examples. Here's a 2 by 3 matrix. B is 2 by 3, C is 2 by 2. You add matrices the obvious way. You just add them component by component. So A plus B, just add each component. A and B have to be exactly the same size. They're both 2 by 3 so that you can add them. Otherwise you simply can't add them. Scalar multiplication, you multiply a matrix by a scalar. You just multiply each component by the scalar, so that's pretty obvious too. Matrix multiplication is a little different. You don't just multiply the components, but we'll talk about that in a minute. So vectors can be considered as n by 1 matrices, so we'll normally, if we think of a vector as being a matrix, it will be a column, not a row. In other words, it'll be a n by 1 and not a 1 by n. It's a vertical matrix. In section 2, we learned how to reduce a system of linear equations down to reduced echelon form. For example, suppose you had a system of 2 equations and 4 unknowns with a 0 right-hand side. This is the right-hand side vector here. After reducing it to echelon form, it might have a form like this, where the columns with the 1s and 0s are solved, their variables are solved for in terms of the others. So this is equivalent to the original system, and this first equation can be written as x1 minus x3 minus 3x4 equals 0. You take the minus x3 minus 3x4 on the other side, and you have x1 is equal to x3 plus 3x4, the minus is changed to plus. x2 becomes minus 2x3 minus x4, and x3 and x4 are the arbitrary variables. You can give those any values you want, 61 minus 83, but x1 and x2 have to have these values. So you can write the solution out in the following form. You say, well, x1 has to be x3 plus 3x4, x2 has to be minus 2x3 minus x4, x3 is just x3, x4 is x4, and so you got everything in terms of the arbitrary variables x3 and x4. Now you separate the x3s from the x4s. We're adding vectors here. It's the same as adding matrices, 4 by 1 matrices here. So first component here is x3 plus 3x4. Second component is minus 2x3 minus x4. Next component is x3 plus 0. Last one 0 plus x4. So you got all the x4s together, x3s. Factor out the scalar x3 out of the first vector. Factor out the scalar x4 out of the second. And you can write the solution in this form. This is an important form. It's called the vector form for the general solution. And you say all solutions of the original system and of this reduced system can be written as some multiple of this vector plus some multiple of that, where x3 and x4 can be absolutely anything. Another example of finding the vector form from the reduced echelon form, and that's the whole point of reducing it down to reduced echelon form, is so you can get this general form. So here's a second example. This matrix has already been reduced. This augmented matrix, this is the right-hand side. I prefer to put a line there to clearly distinguish the right-hand side from the other coefficients of the unknowns. But this is a 3 by 5 system of equations that's been reduced to echelon form, and now x1, x3, and x4 can be solved for in terms of the arbitrary variables x2 and x5. That's the whole point. This makes it easy to solve for these 3 variables, x1, x3, and x4, in terms of these variables, x2 and x5. And x1 is just 3 plus 2x2 minus 2x5. x2 is 2 plus 1x5. 4 is minus 4 minus 3x5. And so x1, x3, and x4 can be written in terms of x2 and x5. x2 and x5, of course, can be written in terms of x2 and x5. They're just x2 and x5. And so you separate out now the constant ones that aren't multiplied by any x, 3, 0, 2, minus 4, 0, and then the multiples, the x2s, and then the x5s, separate those out. Factor out x2 out of this vector, factor x5 out of that, and you got the general form of the equations, and you can say that the solution of the reduced system, and therefore the solution of the original system, is just this vector plus anything times that vector plus anything times that vector. You can plug in any value, whatever, for x2 and x5, and you'll get a solution, and all solutions can be written like this for some x2 and x5, so that's called the general solution. Now, often, if there's a unique solution, then these two terms won't appear. You'll just have that solution. Okay, you can take the dot product of two vectors. We'll talk about that more in chapter 2, but that's the scalar product or dot product of two vectors. It's just a number, which is the u1 dotted with u dotted with v is u1 v1 plus u2 v2, etc. up through un vn. So dot product of u and v would be 2 times minus 4, which is minus 8, plus 3 times 2, which is 6, plus minus 1 times 3, it's minus 3. Add that up and you get minus 5. Now, matrix multiplication is not what you might expect at first glance. You don't just multiply the components. It's very different. You can multiply two matrices. Let's say A times B equals C, and the ijth element of the product is the dot product of the ith row of A and the jth column of B. So Cij is just the dot product of this row with that vector. And since to take the dot product of two vectors, they have to have the same length, that means that the length of this row, i.e. the number of columns in A, have to be equal to the length of this column, which is the number of rows of B. So if A is m by n and B is n by s, then those two have to be the same, otherwise you simply can't multiply them. So A and B don't have to be the same size, but the number of columns of the first matrix have to be the same as the number of rows in the second one. And if they are, the product will be m by s, because there are m rows here and n columns, so you can get an s columns, m by s matrix. So that's what this says. Then the ijth element here is just the dot product of the ith row of A and the jth column of B. For example, if we multiply these two matrices, we can multiply them because the number of columns of the first matrix is equal to the number of rows of the second one. So if you take dot product of rows with columns, you can do that. So the first element and the product, the element in the first row, first column, is the dot product of first row with first column. So it's 2 times minus 1 plus 1 times 0 plus minus 3 times 2, which is minus 8. And the minus 2, where does that come from? It's the dot product of the first, well, the element in the first row, second column of the product is the dot product of first row of A, second column of B. So it's the dot product of this with that. So it's 2 times 2, which is 4, minus 3 is minus 2. Now, if we have an application of matrices here is if you have a linear system, we represent it sometimes by an augmented matrix, but you can also represent it in the form AX equals B, where A are the coefficients of the x's and B is the right-hand side vector, because, for example, this linear system here is equivalent to A times x equals B. because what is A times X? It's the first element is a dot product of first row with first only column of X, so it'd be 1 times X1 plus 3 times X2 minus X3 is equal to 2. And then the second component of AX is the dot product of second row with first and only column, 2x1 plus 5x2 minus x3, and that's got to be equal to second component B is 6, and so forth. So we'll often write a linear system as AX equals B, where X are the unknowns, and B is the right-hand side, and A are the coefficients, 1, 3, minus 1, 2, 5, minus 1, 2, 8, minus 2, and so forth. In the next section, 6, we define the transpose of a matrix basically just by flipping it along the axis. And so if A is this matrix, its transpose, the rows become the columns. First row becomes the first column of A transpose, second row becomes second column. So you just flip it. And if A is n by m, A transpose is m by n. And A is called symmetric if A is equal to its transpose. So to be symmetric, it's got to be square, because when you take the transpose, it has to be square for it to even be the right size. And the elements have to be reflected along the diagonal. For example, here's a symmetric matrix because those two elements are equal. When you take the transpose, it doesn't change, whereas this one, those two elements are not equal, so take the transpose, they're not the same, so B is not symmetric. We're going to look at some of the properties of matrices with MATLAB in just a moment, but let me finish this section here. Okay, the identity matrix is a matrix, square matrix that has ones down the diagonal and 0 everywhere else. It's special. It's kind of like a 1. You multiply any matrix by the identity and it doesn't change. The 0 matrix has all zeros. You add the 0 matrix to any matrix and it doesn't change. Notice sometimes we'll write the dot product or scalar product of two vectors, since we're thinking of vectors as being columns, n by 1 matrices, 3 by 1 matrices, then x dotted with y can be written as x transpose y, not xy transpose, x transpose y, because y is a 3 by 1 vector, x is a 3 by 1 vector, but x transpose is 1 by 3. So you can think of this as matrix multiplication of a 1 by 3 matrix times a 3 by 1, and that'll give you a 1 by 1 matrix, i.e. a scalar, which is just the dot product of the first and only row with first and only column. So we can write the scalar product of x and y as x transpose y. And finally, we define the norm of a vector as the square root of x dotted with itself. So you take the sum of x dotted with itself just means the sum of squares of the components of x. Square root of that is the norm. One property of matrix operations that we didn't mention, is shown in the book, is that the transpose of a product is the product of the transposes in reverse order. So AB transpose is not A transpose B transpose, it's B transpose A transpose, and the order matters because matrix multiplication is not commutative. And there's a proof in the book, but this one is a little easier to follow, I think, although we'll illustrate it using MATLAB. So matrix multiplication in general, the ijth component of the product of A and B, let's say A is n by L and B is L by M, so you can multiply them. That is the number of columns in A, same as number of rows in B, L, and therefore AB will be an n by M matrix. And the ijth component of the product is the dot product of the ith row of A with the jth column of B. So the proof that AB transpose is B transpose A transpose is here. Take the ijth component of AB transpose. That's the jith element of AB, because transpose just switches the row and column. So ijth element of AB transpose is the jith element of AB. So what is the jith element of AB? Well, Here's the ijth element of AB. The jith element, you just switch the I and the j, so this would be ajk times bki. That's what we have there. Just switch the I and j from what we have here. And now bki can be written as B transpose ik, and ajk can be written as A transpose kj. And that is just the ijth element of the product of B transpose A transpose. And so the ijth element of AB transpose is the same as ijth element of B transpose A transpose for any I and j. Therefore, those are the same matrices. Okay, now let's illustrate some of these properties of matrix operations using MATLAB, which is a widely used system that makes matrix multiplication and matrix operations very simple. I've created 4 matrices, just chose elements pretty much at random. A, B, and C are 3 by 3 matrices. D is a 3 by 4 matrix. And we mentioned that matrix multiplication is not commutative. Matrix addition is, of course. A plus B is the same as B plus A. That's obvious because you're just adding the components. It doesn't matter what order you add them. Matrix multiplication is not commutative, however, because see, A times B in this example is not the same as B times A. So that proves they're not equal in general. All you need is one example to show that they're not, but they're usually not the same. You can see that these 2 matrices are not the same. In fact, sometimes you can multiply A times B and you can't even multiply B times A. A and B are 3 by 3, so you can multiply in either order. It doesn't give the same answer. But A times D is, say A is 3 by 3, D is 3 by 4, so you can multiply it and you get a 3 by 4. But D times A is not even defined. So in general, matrix multiplication is not commutative. However, it is associative. What does that mean? That means you can take, if you want A times B times C, it doesn't matter whether you do the AB first and then C, or A and then the BC first and then the A, as long as you're in the right order, A, B, C. So the parentheses tells MATLAB to first do the A times B and then multiply on the right by C. And here we do B times C and then multiply on the left by A, and you get the same thing. That doesn't prove it's associative. Proof is harder, but kind of convincing because we just chose A, B, and C at random. So it really doesn't, you don't even need the parentheses there because MATLAB knows it doesn't matter whether you do the B times C first or the A times B first. So the order from left to right matters, but the order in time doesn't matter. Now let's illustrate the fact that the transpose of a product is a product of the transposes in reverse order, which we just proved. So A times B transpose, the prime means transpose in MATLAB. So A times B, you take the transpose of that. And notice that is not the same as A transpose times B transpose. That's not the same matrix. However, it is the same as B transpose A transpose. See this AB, that means do the product and then flip it. And this says take the transpose of B and multiply on the left by A transpose. So the transpose of product is product transposes, but only in reverse order. Now, of course, matrix addition is also associative. In MATLAB, EYE of 3 is the 3 by 3 identity matrix, and you can take any of those 3 by 3 matrices and multiply by the 3 by 3 identity on either side, and it doesn't change A. Here's the original A. Multiply on the left or the right by the identity. It doesn't change it. Let's take 2 vectors. Let's say U is the vector We're just going to make it a 3 by 1 matrix. So there's U, and let's let V be another 3 by 1 matrix. Just choosing elements at random. Now U transpose times V is just a scalar. That's the dot product. That's see, U transpose is this, row vector V is that. So U transpose times V is that 1 by 3 matrix times the 3 by 1 matrix, which you can multiply and it gives you a 1 by 1 matrix, i.e. a scalar. However, U times V transpose is not a scalar, it's a 3 by 3 matrix, because now you're multiplying a 1 by 3, a 3 by 1 times a 1 by 3, so you get a 3 by 3 matrix. And if you take U dotted with itself, that's the square of the norm of U. In other words, U, the norm of U is the square root of the sum of squares. Remember, U was 3, 1, minus 1, so 3 squared plus 1 squared plus 1 squared is 11. So that's U dotted with U is the square of the norm of U. D is, we find that as a 3 by 4 matrix. D transpose is 4 by 3. You just take the rows, become the columns. So it's not a square matrix, so it can't possibly be symmetric. A is square matrix, but it's not symmetric either, because A transpose is not the same as A. And one more thing, forgot to illustrate scalar multiplication. So here's the matrix A. If I multiply that by 3, that just multiplies each component of A by 3.